الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. أبنائي الأعزاء, in the current lecture inshallah we'll discuss together some sketches, graphs, problems on the logarithmic and exponential functions. These problems are based on the standard forms of the graphs of the exponential and logarithmic function. Let me remind you with the basic standard forms of the exponential and the logarithmic graphs of these functions. As you remember, we have three functions, three exponential functions: e to x, e to minus x, and generally a to x. This is e to x, has the x-axis as a horizontal asymptote. This point is 0, 1. As x goes to infinity, e to x goes to infinity. As x goes to minus infinity, e to x goes to 0. Also, e to minus x, as you remember, is the reciprocal. E to minus x is the reciprocal of e to x. Actually, both are image each other around the y-axis. E to minus x has such a graph. Still, the x-axis is a horizontal asymptote. This point also 0, 1. As x goes to infinity, e to minus x goes to 0. As x goes to minus infinity, e to minus x goes to infinity. Okay? And generally, a to x is the same form as the previous ones. A or x. If a is 1, we have a straight line parallel to x-axis, y equals 1. If a equals 1, the same point as before, 0, 1. For example, if a equals 2, we have such a curve. A equals 2. Still, the x-axis is horizontal asymptote. If a equals 3, we have such a curve. A equals 3. A equals half below A equals half, and so on. Finally, the logarithmic function y equals ln x, as you remember, has the y-axis as its asymptote because it is the inverse of y equals e to x. And its graph, this is ln x, y equals ln x, is something like this. This point is 1, 0. As x goes to infinity, then x goes to infinity. As x approaches 0, then x approaches minus infinity. Okay? As I always tell you, always remember e to minus infinity equals 0, e to 0 equals 1, e to infinity equals infinity, ln 0 equals minus infinity, ln 1 equals 0, ln infinity equals infinity. Okay? Now let us discuss some problems sketching the graph of some given functions. First function, y equals 3 ln x. As we discussed before, this is the function ln x, but it is multiplied by 3, so we have the same graph of ln x but stretched by a factor of 3. If you remember, we studied before the lesson operations on functions. So we have the same graph of ln x but stretched, every value is stretched 3 because of the factor 3. So we draw the same graph of ln x but taking account that it is stretched 3. The standard form of ln is this. This is the standard form of ln. Okay? I'll draw the graph compared with the standard form. 0 is still 0. When you multiply 0 by 3, it is 0. So, but other values will be stretched 3. This is y equals 3 ln x. Such a graph. The same form. This is still 1, 0. This is ln x. This is 3 ln x. Okay? Both have the y-axis as a vertical asymptote. Both have the y-axis as a vertical asymptote. For in the positive part, 3 ln x higher than ln x. In the negative part, the 3 ln x deeper than y equals ln x. Okay, this is the original one. Okay, another problem, ln 2x, y equals ln 2x. As we know, when this value is 1, ln 1 is 0. This value is 1 when x equals half. So in the standard curve, when equals 1, ln x equals 0. Now it is replaced by half. Okay, so I ask you always to keep these values in your mind. If the argument of ln is 1, so it's the value of ln is 0. Now the argument of ln is 2x. If 2x is 1, ln 2x is 0. 2x is 1 if x equals half. So instead of 1 and 0, it will be half and 0. And the new graph will be something like this. Still similar, we don't draw point by point, but we have a sketch. we have a sketch of the graph. How it looks like. This is the idea. Okay. Still, the y-axis. Still, y-axis is a vertical asymptote. The y-axis is a vertical asymptote. The y-axis is a vertical asymptote. Okay, and the curve will be like this. This point is half and 0. Okay, x, y. Okay, but if you want to compare, with the original curve, how it looks like. As you remember, len x would be start here. It would intersect the x-axis here. Okay. Also, we have a third curve to discuss. y equals len x minus 1. Okay, y equals len x minus 1. This is f of x minus 1. This means that, if you remember, we have said before, shift to right, shift to left. If you remember, shift upward, shift downward. Now we take from the values of the function 1, so it is shift downward. Okay, so if the original curve was like this, this is, as you remember, 1, 0. So this curve will be shifted downward. This curve will be shifted downward, or the x-axis is shifted upward. Okay, this curve will be shifted. This is the original curve, y equals len x. This is the red curve. This one is y equals len x. Okay, now, as you know, the y equals 0 if this value is 0. So when len x is 1 minus 1 is 0. So when len x is 1, when x is e. So for the new curve, the point of intersection with the x-axis is at x equals e. Okay, this will be verified, as I told you a few seconds ago. This means a shift of the red curve either downward by 1 or shift of the x-axis upward 1. Now the new curve will be something like this. But this point, still we have the y-axis a vertical asymptote. This is a vertical asymptote. Now this point is e and 0. If you have a vertical line from this point to here, this point here is E and 1. This point is here. Also, if we have a straight line from here, this point is 1 and minus 1. Okay? So, when you shift this downward by 1, 1 will be 0. When you shift this point downward by 1, the 0 will be minus 1. So, this is our graph y equals ln x minus 1 compared. When you draw, you don't need to draw the original curve, but I draw the original curve to compare it to give you some sense about the new graph and the original graph. But when you draw only this one. You draw only this one. You draw only this one. Okay? But I compare with the original curve to give you some sense about what happened for the original curve. Okay? Also, we want to discuss the graph of the curve y equals ln absolute value of x. As we know, the function ln x exists if and only if the argument x is positive. Now, the argument of ln x is absolute value of x, so it is always x is always positive. This function can be redefined as follows: ln x if x greater than 0, so where x is positive, and ln minus x if x less than 0. Why? When x is less than 0 means negative. Negative with negative will give you a positive argument. Okay, so our function y equals ln x is actually two definitions of the function ln x. So we have ln x to the right and ln minus x to the left. So our curve will be like this. The same standard form to the right and its image to the left of the y-axis. This is the original y. We have the y-axis as a vertical asymptote. Okay. And for x greater than 0, we have such a curve. This is 1, 0. For x less than 0, we have such a curve. This is minus 1, 0. To check, set x minus 1, minus 1 is 0. Okay, this is ln x and this is ln minus x. Okay, and both are ln absolute value of x. Okay, this is 1, 0, infinity, infinity. This is 0 minus infinity, actually 0 plus. This is 0 minus and minus infinity, and this is minus infinity and infinity. Okay, as you see, piece of cake. Okay, want to discuss the graph of the curve y equals ln x plus 2. Also, this operation is the original function ln x, where x is replaced by x plus 2. Okay, so if you remember, this is what we called before shift to the right, shift to the left. This is shift to the left, okay, or shift of the y-axis to the right. By what? Here shift of x to the left by 2, shift of the curve to the left of the y-axis by 2, or you can shift the original y-axis to the right by 2. Okay, let us draw first the original curve and compare with the new curve. Okay, let us draw the original curve. This is so to make use of this lecture, actually you have to remind yourself with the lecture of operations on functions. Okay, this is left shift of the function. If it was lim x minus 2, it is a right shift of the function. Okay, this what we are dealing with lim x, so the y-axis is a vertical asymptote. This is the original curve, lim x. This is the original one. Y equals lim x. Okay, this is the original one. This point is 1, 0. Okay, now what about x equals to, we shift to the left, by 2. So this point will be minus 1 and 0. Okay, and the new curve will be like this. Which will have, as you see, this the difference between the distance between the vertical asymptote and the point of intersection with the x-axis is 1. So we have to go 1 out to the left to obtain the vertical asymptote. So the vertical asymptote now will be at x equals 2. New vertical asymptote will be like this. 2 to the left means minus 2. To the left means x equals minus 2. Okay, so the curve will be like this. What about this point? This point where x equals 0. So this point is 0 and lim 2. This point is 0 and lim 2. Okay? We shifted every point on the curve to the left. Okay? Every point. So this also shifted to the left 2. So the curve is like this. This point is minus 1 and 0. Okay, and this line is x equals minus 2. Okay, remember the intersection of the lim x with the x-axis is far away 1 from its vertical asymptote. this point, intersection of y equals an x plus 2 with the x-axis, so far away from it by 1 obtains the vertical asymptote. This is minus 1, so the vertical asymptote is as x at x equals minus 2. Okay, as I told you, this only a guide curve for you, but when you draw this only, but just I make a comparison with the original curve to give you some more sense or more understanding for the sketch. Okay, we solved it, as you see, many problems with ln x. Let us draw some or sketch some curves including the exponential functions. First function we have to draw is y equals e to half ln x. Piece of cake. How? It is e ln x power half, or e ln root x. E cancels ln, so it is root x. Actually, the curve is not exponential, is not logarithmic, but it is a square root of x. So the curve simply will be like this. Don't let him deceive you. Take care of the problem, understand carefully and understand well what you are dealing with, so you can operate in the most efficient way. This is x, this is y equals root x. Okay, root x is the inverse of y equals x squared. Root x is the inverse of y equals x squared. Okay, another problem, y equals x squared. Y equals e to x squared. Y equals e to x squared. Oh, let us look carefully at the problem. E, so it is an exponential function. X squared, this means that if x is replaced by minus x, we have the same value. As you see, y of minus x is still e to x squared. That means that y of x. So y equals f of x is an even function. Okay, so the y-axis is a mirror for the function, from right to left or from left to right. So just draw in one side, you can draw the other side. Our axes are y and x. This is the x-axis. This is the y-axis. Okay, e to x squared. If x equals 0, e to 0 is 1. Very simple. This point is 0, 1. As x increases, y increases. As x increases, y increases. Okay? So x increases, y increases, 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 and so on. But this function is even, so the other side is the same. Now, one may ask, why you didn't state the horizontal asymptote? Okay? As x approaches infinity, e to infinity is infinity, not a number to stop at. As x approaches minus infinity, e to minus infinity all squared is infinity. So the horizontal asymptote, if the function at x equals infinity reaches a certain value, y is some value. But here, as x approaches infinity, y goes to infinity. As x minus infinity, y goes to infinity. So I don't have any asymptotes. This for the horizontal asymptote, but the vertical asymptotes, if you have a rational function and its denominator is 0. This is not a rational function. This is not a rational function. Okay? And its denominator, it has no denominator. Okay? So it is has no asymptotes, neither horizontal, neither vertical. Okay? But ln x is also not a rational function, but it has a vertical asymptote. Yes, this is a very good question. Ln x is the inverse of e to x. Ln x is the inverse of e to x. E to x has a horizontal asymptote. When x approaches minus infinity, e to x goes to 0. E to x has, this is e to x. As x approaches minus infinity, e to x approaches 0. A specific value for y. So y equals 0 is a horizontal asymptote for e to x. But ln x is the inverse of e to x. So ln x has the y-axis or x equals 0 as a vertical asymptote. This is why ln has a vertical asymptote in spite of not being a rational function. Okay? Another problem, we want to draw e to minus x squared. E to minus x squared. We already draw y equals x squared, e to x squared. We already draw y equals e to x squared. Now we need to draw e to minus x squared. Few seconds ago we draw e to x squared like this. I'll redraw it as a guide curve to make use of it to draw the new problem. In other words, I use a previous information to solve a current problem. I use a previous information to solve a current problem. This is, as you see before, just a few seconds ago, this is e to x squared, this one. Now we need to draw e to minus x squared. E to minus x squared, which is 1 over e to x squared. The reciprocal المقلوب as this is 0 1. This is 0 1. The reciprocal of 1 is still 1. Now as x increases, e to x increases, e to x squared increases. So it's like this. But here, as x increases, e to x squared decreases. This increases, its reciprocal decreases. As this goes to infinity, this goes to 0. Also the same in the other side. That means the x-axis is a horizontal asymptote. Why? Very simple. As e minus x squared, e to minus x squared, as x approaches plus or minus infinity, e to minus x squared approaches 0. This is why. Y equals 0 is the x-axis. Okay, so this is e to minus x squared. The red one is e to x squared. This is e to x squared, and this is e to minus x squared, which is the reciprocal of the red one. Okay, okay, we want to draw e to 1 over x squared. 1 e to 1 over x squared. E to 1 over x squared. Okay, this is x, this is y. Okay, we have here a serious situation, موقف خطير. What? 1 over x squared. As I told you, we have to take care when we have a denominator, especially when this denominator can be 0. X can be 0 on the y-axis. 1 over 0 is infinity. But we studied the limits. We have a very strong and powerful course in limits. 0 includes 0 plus, 0 minus. Just after 0, just before 0. Just after 0, just before 0. Just after 0, we have positive values. Just at 0, but just after it. 1 over 0 is infinity. So at 0 plus, this function goes to infinity. Limit e to 1 over x squared as x approaches 0 plus is infinity. What about limit e to 1 over x squared as x approaches 0 minus? Yes, x in this side to the left of the y-axis, x is negative, but you have x squared, which will go to positive values. So still this value will also be infinity. At 0 minus, yes, 1 over x is minus infinity. 1 over x is minus infinity at 0 minus. But we have 1 over x squared. When you square in minus infinity, it is infinity. So either to the left of the y-axis or to the right of the y-axis at 0, the function e to x squared goes to infinity. So we have here infinity, we have here infinity. Okay? Now, as x increases with positive values, negative values, this is still positive. So no part of this curve under the x-axis. This curve is always positive, and it is still even function like this. Still even function like this. Okay? As x increases, y decreases. Y decreases, y decreases. As x approaches infinity, 1 over infinity is 0, e to 0 is 1. As x approaches minus infinity, this will be plus infinity. 1 over infinity is 0, e to 0 is also 1. So, in both cases, when x approaches infinity or minus infinity, this part is 1 over infinity, which is 0. E to 0 is 1, so we have y equals 1 is a horizontal asymptote. Y equals 1 is a horizontal asymptote. as you see, we finished limits in 1 month ago, but we still have its effect with us. As I told you, the study of mathematics is a cumulative one. You can't ignore anything you studied before in mathematics. Take care of this. Now, the curve continue, the curve continue, and so on. This is y equals 1. Okay? A new problem, y equals e to x cubed. X cubed odd. So this function is odd? No. Why? Here, when you replace x minus x, yes, if this is f of x, so f of minus x equals e to minus x all cubed, which is e to minus x cubed. Is this equals the original function with negative sign? Original function is e to x cubed with negative sign. Is this equal this? No. So this doesn't equal minus f of x. Therefore, the given f of x is not an odd function. But few seconds ago, f of x equals e to x squared or e to minus e to 1 over x squared were both even function. Both were even function. Yes. Why? Because f of minus x equals e to minus x all squared or e to 1 over minus x all squared, which is e to x squared, which is e to 1 over x squared, which is the original function f of x. So the sign doesn't matter. F of x, the original function, or g of x, for example, another one. Okay? So e to x squared and e to 1 over x squared are even function. But e to x cubed is not. Even e to x, as you remember, neither even nor odd. And when we obtained e to minus x, it wasn't the odd form of e to x. No, it wasn't. If you remember, okay, neither even, neither odd. E to x, if you remember, was like this. This one was like this. Okay? Any odd function needs some values of function to be negative. Odd function needs some of the values of function to be negative. But both e to x and e to minus x are positive. So how come they can be odd functions? Okay? Let us go back to our problem. Y equals e to x cubed. Okay? Before drawing the function, let us take some information of it. When x equals 0, this function will be e to 0 is 1. Okay? When x equals 1, this function will be e. If we have x e to x cubed. 0, this function is 1. 1, this function is e. Minus 1, this function is e to minus 1. Okay? Infinity, this function is infinity. Minus infinity, this function is 0. E to x. When x is 0, this function is 1. When x is 1, this function is e. When x minus 1, this function is e to minus 1. When x is infinity, this is infinity. When x minus infinity, this is 0. What you want to say? I want to say that this function is not completely a new one. It can be easily compared with the well-known function to us. It has the same behavior of e to x at a set of values. As x is 0, 1, 1, so this function passes through the point 0, 1 here. As x equals 1, both are the same. So they intersect at the same point. 1 for x, e for y. And the third point, minus 1 for x and e to minus 1 for y, e to minus 1 for y. So this function intersects 3 times with e to x. E to x cubed intersects 3 times with e to x. And they have the same behavior of e to x as x approaches infinity, as x approaches minus infinity. Okay? So I already draw it for you in a very clear graph to show you. The dashed curve is e to x. The solid curve, red solid curve, is e to x cubed. As I told you few moments ago, they have the same values of x and y at 3 points. Same values of x and y, this means that they intersect at these points. They intersect at x equals 0 and y equals 1. They intersect at x equals 1 and y equals a. They intersect at x equals minus 1 and y equals e to minus 1. These are the 3 points where they intersect, as you see. So if we put the two curves in the same graph, as I told you, I draw the original curve y equals e to x just as a guide curve to help me to deduce the new graph of the given problem. Okay? So when I solve some problem, you can make use, as I told you, of an old information to help you to deduce the optimum solution of your problem. X, y, which is in our problem e to x cubed. Okay? Our problem, as I told you, have the same behavior of e to x. Okay? As x approaches infinity, e to x approaches infinity. As x approaches minus infinity, okay, so it has the same behavior. So it will be like this. Okay? And as I told you, it will intersect with this point is 0, 1. This point is 0, 1. Okay. Another important point for us. another important point for us. Okay, another important point for us is 1 and e to 1. A third point is minus 1 and e to minus 1. The original curve e to x will pass through also with these 3 points, but as I told you, it is a guide curve, and this is e to x cubed as we need. Okay, now we'll enter a new type of problems. Y equals e to x times sin x. E to x times sin x. You want to draw this curve. Okay? You want to draw this curve. E to x is something like this. This is e to x. This is e to x. Okay? This is e to x. Sin x is like this. This is sin x. Nice. We want to draw the product of e to x times sin x. Again, this is e to x. This is sin x. We need this times this. Let us prepare our problem before solving it. As you see, sin x, somewhere it is 0, another where it is 1 or minus 1. Okay? Now, 0, 0, 0, at 0, at pi, at 2 pi, at minus pi, at minus 2, and so on. When sin multiplied by e, at this point, 0, pi, 2 pi, minus pi, the product of these two functions will be 0. Okay? So, the new function, e to x times sin x, has intersection with the x-axis at 0, pi, 2 pi, minus pi, minus y, or n pi. Okay? When sin is positive, the product is positive. When sin is negative, the product is negative, because e to x is always positive. So, from 0 to pi, the product is positive. From pi to pi, the product is negative. From minus pi to 0, the product is negative. From minus pi to minus 2 pi, the product is positive. Okay? So the product of the two functions is some intervals positive, other intervals negative. Okay? At pi by 2, at 3 pi by 2, 5 pi by 2, minus 3 pi by 2, minus 5 pi by 2, sine is positive. The sine is equal plus 1. Sine equal plus 1. When multiplied by e to x, it gives the same value. But at other points, minus pi by 2, 3 pi by 2, minus 5 pi by 2, sorry, excuse me. Sine is minus 1, so the product will be that of E but with negative 1. Again, sine somewhere positive, somewhere negative, so the product of the two functions is somewhere positive, another where it's negative. But it's well defined, when positive, when negative. Okay? Sine at specific points is 0, as you see. So the product will be 0. Okay? E to x is increasing from 0 to infinity. Is increasing from 0 to infinity. But sine x is bounded between minus 1 and 1. When you multiply bounded value with increasing value, the product is also increasing. Still increasing. Because it's bounded between minus 1 and 1. But this is increasing. It will reach, inshallah, infinity. So the product is increasing. Where it is positive, sine is positive, the product is positive. Where it is negative, the product is negative. But at some point, remember, the product is 0, okay? And at some point, the product is that of E, where E to x, where sine x is 1, minus 1, the product will be that of E to x, but E to x by its sine, E to x with negative sign. So the product will be something like this, as you see. 0 where sine is 0, as you see. Since E to x is increasing, as you see, it increases. When we have positive interval of sine, the product is positive. When we have negative interval of sine, the product is negative. Okay? Okay. So, drawing the graph of E, x times sine x, will have the following shape. Something like this. These points are 0, pi, 2 pi, 3 pi, minus pi, minus 2 pi. This as pi by 2, 3 pi by 2, 5 pi by 2, and so on. Minus pi by 2, minus 3 pi by 2. This point is e to pi by 2. Sine pi by 2 is 1. This point is e to 5 pi by 2 times sine by 5 by 2, which is 1. This point is minus pi by 2. This for y. This for y. It means this value is for y. Here x minus pi by 2. Of which sine is minus 1, and y, which is with e to x times minus 1, would be minus this value here, minus e to minus pi by 2. X is minus 3 pi by 2, x. But y is e to minus 3 pi by 2 and so on. This is 3 pi minus 3 pi and so on. Okay? Again, what about e to x cosine x? As we said before, this is e to x, this is cosine x. Cosine, periodic function, alternates between -1 and 1, as you see, intersects with the x-axis at some points where cosine is 0. So when we multiply e with cosine, we'll multiply e with cosine. Okay? This is e. This is e to x. This is sine x. Cosine x. This is cosine x. Okay? This is e to x. This is cosine x. Okay? As we said before, when cosine is 0, the product is 0. So, e to x times cosine x will be 0 and pi by 2 minus pi by 2. Here, 3 pi by 2 minus 3 pi by 2. 5 pi by 2 minus 5 by 2. Okay? Add 0 add 2 pi minus 2 pi, cosine is 1. So the product is that of e at these points. Add pi minus pi, 3 pi minus 3 pi, cosine is -1. So at these values of x, the product is that of e to x. Okay? So the product would be like this. Where cosine is 0, the product is 0, as you see. Where cosine is positive, the product is positive. Where cosine is negative, the product is negative. Where cosine is 1, the product is that of e to x. Here, 1, 1, so this point is 0, 1, 0, 1. This point is 0, 1. This point is 0, 1. Also this point is 0, 1. Okay? This point is pi and -1. So we'll multiply by this. This will be e to pi with negative sign. This point. So actually, this point is pi for x and minus e to pi for y. Okay? This point here, cosine is 1 and the x is 2 pi. X is 2 pi. So this point, 2 pi for x, 2 pi for x, and for the product, cosine will be 1, so it is e to 2 pi. And so on. The same like this curve, the same like this curve, as you see, but we'll start with a value at the origin, not 0 sign, because sign at the origin was 0. Sign at the origin was 0, so 0 times 1 will be 0. But in case of cosine at the origin, cosine is 1, so 1 times 1 is 1. Okay? So the curve of e to x, this is e to x, this is sine x, this is e to x times sine x. Okay? While This is e to x times cosine x. This is e to x times cosine x. This one, okay, would be something like this. Actually, the e to x touches here. E to x touches here. E to x touches the curve here. Actually, this is e to x. Also, in case of sine, e to x touches here. Okay? Now, after discussing this set of problems, we will finish with some fruits. And I hope you will make use of this function and it will be useful for you, inshallah. We have 4 graphs and 4 equations, and we need us to match these graphs we need to match these graphs with the given equations. Okay, let us discuss these problems. Now, as you see, look at the graph and look at the equations and the match one with another. Okay, which one you will start with? Which one you will start with? A or B or C or D? For me, I start with C or D and I leave A and B after finishing this. Why? Because I know that len intersects the x-axis at 1. This. Okay? So, this is similar to len, but it is with negative values. As you remember, len was like this. Len was like this. If you remember. So, actually, I have equation y equals minus len x. Y equals minus len x. So, 2 matches D. So, 2 matches D. Because actually it is len, but multiplied by negative 1. This. Okay? Okay. Few moments ago, we discussed the curve y equals len modulus x. Len modulus x. You remember? Let us bring this problem. Y. Let us. I'm looking before. Yes. It is this. Okay. This is len, as you see. This is negative len. Okay. When I ask you to obtain this function multiplied by minus, this will be upward and this will be downward. So it will be something like this. Which is this? Oh, I have actually here y equals minus len minus x. So C matches 3. So now 2 matches D and the 3 matches C. Okay? Because len minus x was originally like this. This is len minus x. Multiplied multiplied by -1, so it is this shape. Now, what about A and B? We discussed a problem similar to this. And similar to this. X minus 1, as you remember, this means shift to the right. X minus 1 by 1. As you remember, if the argument of len is 1, the argument of len is 1, len will be 0. X minus 1 is 1 if x is 2. If x is 2, y, which is len 2 minus 1, len 1 will be 0. This one, as you see. And the vertical asymptote appears when the argument is 0. The argument is 0 when x is 1. This one. So 4 matches A. From two signs, من علامتين. The first sign, when x is 1, the len is 0. Now we have len x minus 1. How come x minus 1 is 1 if x is 2? If x is 2, we have len 2 minus 1, which is len 1, so the curve with y equals len x minus 1 will passes through the x-axis, which is this one. Okay? So 4 matches A. So by default 1 will matches B. Can you prove? Yes. 2 plus len x is shift upward. 2 plus len x is shift upward by 2. Okay? This value, as you see, when y is 0, when y is 0, when len x equals minus 2. When len x equals minus 2. So minus 2 plus 2 gives you, so this point, as you see, will be e to minus 2. Why? This point e to minus 2. Why? Because when x equals e to minus 2, here we have len e to minus 2. Okay? So you drop minus 2 outside, so you have len e, which is 1. 2 minus 2 will give y 0. E to minus 2 equals 1 over e to 2. Means 1 over, so the whole value will be less than 1, which is this one. Okay? And normally when x is 0, len 0 is minus infinity, so still the y-axis is vertical asymptote. Finally, we have a set to match with the exponential function. This is the last set of graphs. We have four equations with 4 graphs, and we want to match together. Which one we start with? Simple equations. This is e to minus, as you see. This is e to minus, as you see. But as given, at x equals 0, the curve passes through 0, 2. Here, at x equals 0, y equals c. At x equals 0, y equals c. For e to 0 is 1. So as you see, c will be 2. This is for equation 1. This is for equation 1. Okay, so equation 1 matches this graph. Say we have graph A, graph B, graph C, graph D. So equation 1 is matches with graph C, and the value of C is 2. Now this has the shape of e to minus x, this one. Also at x equals 0, c will be 2. Here this is the value of c. Now what about this? What about this? Which one matches with Let us discuss. Take care, this goes to infinity, minus infinity. May the graph deceives you? No. This go to minus infinity. Which one? We need the graph to pass through the origin. This means that when x is 0, y must be 0. We finished from 1 and 2. 2 is D and 1 is C. Now, if we set x is 0, e to 0 is 1, 1 plus 1 is 2. So it is C over 2. But when x is 0, e to 0 is 1, 1 minus 1 is 0. So 3 will be matches with A. But I want to check these values, negative values. Yes. As you know, e to minus x, this one, is increasing with negative values of x. E to minus x is increasing. Take care. K and C are positive values. K and C are positive values. Okay? Also in the previous problem. Here, as x goes through negative values, e to minus x increases too much. More than 1. 1 minus more than 1 is negative, so it has this shape. So 1 is matches with A, and finally 3 will matches with A, and finally 4 will be matches with B. I want to check, I want to prove. Okay, no problem. When x is 0, in case of this, when x is 0, this is 0. So B is not 3. And we already finished from 1 and 2. Already finished. Now we are discussing 3 and 4. But also we finished with 3, which is matches with A. But I want to be sure. When x is 0, y is not 0. Like this. But when x is 0, e to 0 is 1, 1 plus 1 is 2. Actually here, c over 2 is 1, or c is 2. No problem, no problem. As x increases, going to infinity, e to minus infinity is 0. E to minus infinity is 0. So this one, e to minus infinity is 0. So this value is 1. Okay? So y equals c. And few seconds ago we said c is 2, which is 2 actually. This behavior. When x goes to minus infinity, then this will be e to minus infinity, which is e to infinity, which is infinity. Okay, which is infinity. E to infinity is infinity. 1 plus infinity is infinity. C over infinity is 0, which is this. So 4 matches with B. Alhamdulillah, we finished our lecture. Inshallah, we'll enter new subject next lecture titled as hyperbolic and inverse hyperbolic functions. Inshallah. Good luck and best wishes.